Hello, everyone. Welcome to the session number 2 for the ASI seminar. Today we have Zhou and Beatty Chen from CMU. So quick introduction for the speakers. Zhou is a PhD student at CMU, advised by Professor Beatty Chen. His research focuses on LL reasoning, efficiency, and local abilities. And Beatty Chen is a professor at Carnegie Mellon. She works on efficient AI, particularly interested in designing, optimizing algorithms on current hardware, so to accelerate large machine learning systems. And then please, Yang, please take it away.
Okay, thank you so much for inviting me. So let me share a screen. Can you all see the screen, or there's some glitch?
Yes, it works.
Okay, sure. Yeah, again, thank you so much for inviting me to this very second talk of the ASAP seminar. And again, so my name is Zhou, and I'm a second-year PhD student advised by Beatty at CMU. And so the topic of today's talk is actually called GSM-Infinite. How do your LLMs behave over infinitely increasing context length and reasoning complexity? So a brief word before we jump into the motivation of the work is that in this work, we basically make a problem generator capable of generating grade school level math problems that you can have arbitrary context length and also reasoning complexity. We believe like this problem generator, also the synthetic data set benchmark that we will release will be very helpful for both the long context and also the LLM reasoning community, because we believe that it really allows you to kind of probe and also evaluate the large language model behavior with very, very high precision or fine-grained control. So let's get started. So basically, first, we start with motivation. In the past 1 year, I would say, like we have seen that long context LLMs have come a long way in terms of its long context ability. So here I took a screenshot of the, I think this is Gemini 1.5 Pro. This is from their technical report. This screenshot is basically focusing on their ability on context retrieval tasks. So you can see that Gemini 1.5 Pro is getting almost perfect score at text level context retrieval, even up to like say 10 million tokens. In the paper, just for showing their strong performance of long context, they also evaluate tasks, say like multimodality, say audio and video, and also they evaluated say on long document question answering and other tasks. So since we have seen such an amazing performance of long context models, it's really tempting to kind of ask the question, like, what is the ultimate trophy, or what is like the ultimate goal of the long context LLM's development, right? Actually, if we extend this topic a little bit more broad, is like saying, what is like the ultimate goal of any AI agent one day, right? Why are we developing them? I think what we believe is that AI agent will one day solve humanity's most challenging intellectual problems, like solving some unproven mathematical, like proving some unproven mathematical like theorems, or actually make some very helpful scientific discovery. So on the right, I actually show a teasing motivation example. Is that in 1995, Sir Andrew Wiles actually proved Fermat-Last theorem. So we actually use Llama 3 tokenizer to tokenize the entire like proof. And we show that the proof is actually more than 88K tokens. So we argue that if an AI agent is capable of processing, like using the past literature and also generating, such high quality text, it has to have this ability to kind of process a very, very high informationally dense and also tightly connected context, and also be able to generating them. If that is like the requirements, we argue that a mere context level method, say RAG, cannot really capture this deep interconnected logics and semantics. And long context LLMs are extremely promising because it seems that they are the only viable path right now towards a true like intellectual agent. So they're immensely important. We also found that their current long context benchmarks are quite flawed, and we will go into in the following slides. So we really need even higher, more high quality long context benchmark, and also with fine-grained control of both like reasoning complexity and also the context length to really measure kind of the or benchmark and facilitate the development of long context LLMs. So as I mentioned before, we think that the current long context benchmarks are flawed, and their limitations can actually be categorized into these three classes. So to make our discussion a little bit more specific, we kind of pull out this very famous benchmark called Ruler. On the right, we kind of pull out its components of Ruler benchmarks. So the first problem is that we found that most of the tasks, not only in Ruler actually, in most of the existing long context benchmark, they are kind of too simple, meaning that you can go through the task without even need to do any reasoning in terms of the complexity. For example, we can see multiple of these retrieval level tasks and also the QA tasks. So the same pattern also applies for like long bench and also long bench V2. For the second class of limitation is actually many of the tasks that is contained in this benchmark are actually innately short context problems, but they are bloating them up into long context by injecting like semantic irrelevant noises. So a very classic example here is the VT, variable tracking task, where it is basically at its core just a bunch of like clauses of variable assignments, but they also add very random filler text like the sky is blue or the grass is green. Actually, a more recently published benchmark called Babylon is also a similar token. It's like you have these puzzles, which is only a few sentences itself, but you inject PG-19 filler text to it. Yeah. And for the first two type of tasks, we argue that these tasks are not really sufficient to actually show the value of long context because they can be solved by RAG without much difficulty. Yeah. Last but not least, another type of task that is also worth mentioning is we admit that there are some long context benchmark that check all the boxes, but these tasks are usually require huge human labor to verify and also to dedupe. Requires huge human labor to actually formulate them well, and they cannot scaling up easily. And also, we cannot precisely control their difficulty. So, for example, here I mentioned on the slides several coding tasks like SWE bench or Daphne bench. So SWE bench, if you don't know, it's a coding completion task. Daphne bench is code verification tasks. So as you can see, they are very finite. For example, SWE bench only have like 12 repos to choose from, and Daphne bench only have this 700 ground truth. Their tasks are actually highly like complex and also incredibly long. So for example, on average, SW bench is like 438K lines of code, but and also their benchmark cannot be solved by RAG. But as I said, like their benchmark requires huge human labor that cannot be really scaled up, and also are not so approachable for most academic labs because I think most of us only have like resource for say 8 billion models or 70 billion models, but here they are even probing the state-of-the-art kind of regime. So based on the like previously talked about three different drawbacks, we argue that current long context benchmarks cannot really sufficiently evaluate the value of long context LLMs. So to make things a little bit more concrete, here we kind of do a more in-depth case study to really see, how well this close competitor to long context LLM, which is RAG, perform on this previous long context problems. The conclusion is actually incredibly simple: is that our experiments show that RAG, so that, we use the classic construction, which is one retriever plus one decoder, is actually surprisingly strong and robust on existing popular long context benchmark, and reaching scores sometimes very compatible to long context LLMs. So let me reiterate. So the RAG we basically formulate is basically a LLM, and we limit its context. So here we usually limit it to like 2K plus a retriever, and But let us take a second here to like kind of ponder this conclusion, because if that is true, then for all of these, long context QA summarization, all these tasks in real life, you won't want a long context LLM to solve them, because RAG, when you inference RAG, is actually incredibly more efficient, right? Because you're only tokenizing instead of encoding the long chunks during prefilling. And when you generate, your LLMs only need to operate this very limited context instead of this like entire context in long context LLMs. So here are like some more details about the experiments results. So to be more specific, we use a 70B model. As I talked about, we limit its context to 2K, plus a retriever, which is what we use is MPNet base v2. And versus the baseline long context model is the 70B model, which is having this full context. And above, we kind of go through all of the popular long context benchmark. So ruler, long bench v2, and loft. So for each task, we actually compare long context model against two RG baselines. So one is the passive RG, which is just the most simple one is like you pass the query to the retriever, then the retriever go on to give you this 2K context. And also we have this interactive or this active retriever, which is cited here. Basically, what it does is that it allows the decoder to generate the subsequent query to kind of to do iterative RAGs. We limit the number of times to 10. As you can see on the above like chart, or I will call it a figure. Yeah, in the above figure, you can see that RAG is incredibly robust in these tasks we studied. Here we want to be extremely careful and not overclaiming stuff. So there exists tasks where RAG are suboptimal to long context LLMs. For example, the CWE from ruler and also passage count from long bench. So if you are familiar with this task, you probably know that these tasks are innately tasks where you have to have the whole grasp of the entire context, right? CWE is finding the most common words. But we also argue that these tasks are kind of too artificial, so you don't even need a neural network to solve them. So you only need a very very good software. You can solve them with perfect accuracy. One close up. Here is like an even closer look at the strong performance behind RAG system. So here we actually select the very famous VT from ruler. So as I talked about, VT is basically you have this multiple variable assignment clauses and wrap it around with this random generated filler text. Here we actually compute for all chunks in the context. We compute the distance, the semantic distance between the query and the chunk. So this is basically computed by the retriever. So retriever gives a score, and we do the L2 distance. And we rank them from the highest to the lowest. So the highest meaning that retriever think, this chunk is the least relevant to the query, and the shortest or the lowest meaning that the retriever think this is highly relevant. We also so to oracally study, we also manually labeled all of the chunks that are required to solve this problem in orange. So you see these orange chunks are actually, this oracle that you have to retrieve in order to solve the problem. So the conclusion in this slide is that we show that RG is incredibly strong at filter out the noise. So if you only inject like irrelevant noise to your short context problems, the RG is very keen at filtering out all of the irrelevant noises and really reduce the whole long context problem into a short context, which LM can solve it at ease. So yeah, okay, so we talked about the motivation, and now here comes the problem statement. So what we really want to get from so what is like the ideal long context benchmark that we want to solve, right? So ideally, we want this following three like characteristics. First is that we want to really have this controllable and also scalable complexity. By scalable, meaning that we also want it to be future-proof, right? We want So say if 04 comes out, we want to have something that that it can measure on. We also want to have this true long context ability, or this hard to distinguish noise. So we want the context to be RAG proof. Also, we want to have the quantity to be kind of scalable, right? We don't want human, like high human labor at just curating every problem. So the problem now becomes how can we develop such benchmark that check all the boxes, right? So this is actually a facilitating of many of the recent works. We actually are actually inspired by many of the recent work that kind of bridges the math problems versus a more abstract construct, such as a such as a computation graph. So for example, the work I cited here is physics of LM 2.1. So basically, they formulate a very rudimentary connection between a computation graph versus a mathematical problems. So we are very fascinated by it, and we basically continue. We carry on the baton and continue on this path. So here, let's consider this very simple problem of only like explicit operations. So by explicit, meaning that every operations are written as, say, plus or the sum. So we have like 7 lions in this zoo. The number of dogs is given by 5 plus the number of lions, and the number of pigs is the sum of dogs and lions. And what is the number of pigs? You can find out that the actual solution for computing the answer for this question can actually very closely formulated into a computation graph. And we argue that if all the operations are very explicit, meaning that you give out its name, regardless is like the mathematical sign plus, or use some close like natural language token, say sum, they can actually we can actually formulate this one-to-one mapping from the question to the computational graph very easily. So the goal is basically, if you can formulate this mapping, then randomly perturbing the computation graph or randomly generates new computation graph will leads you to generating like, if you map it back, you can generate like a very huge amount of corresponding natural language questions, right? But it turns out that the reality isn't that simple, meaning that we also encounter many of the implicit operations, meaning that your question asks about something, but it doesn't mention that you have to do an addition, or it doesn't have to do a multiply, but you have to carry out that specific operation in answer. So here is a more specific example. So say you have that many dogs in zoo, that many lions. So lions equals to that number of dogs. And then you ask about what is the total number of animals in Jefferson Zoo, right? In whatever zoo. So for human beings, it's very natural because to answer this question, because we know dogs and lions are all animals, right? So we then know that we need to carry out and perform this plus operation. But how would you encode this to a computation graph, and how do you translate a graph into generating such problems remains a challenge. Actually, in GSM-AK, we actually discovered that all of the 4 fundamental operations, so plus, subtract, multiply, and divide, also all have this their corresponding implicit operations in questions. So how to generate them is a challenge. Here we actually used the previous work design of using a abstract instance parameter construct. So the essence is extremely easy. It's saying that we introduce this new node of like this abstract variable, this animal term. And in the computation graph, we actually write everything explicit. We know that we have to perform a sum, so we have this red edges. But when we translate this graph to the actual natural language, we deliberately omit these 2 red edges and just describing every other operations. So basically, it forces whatever it is, the human or the LM to rely on their common sense reasoning to complete the rest of the operations. So this is sum, right? This is implicit sum. but how can we do implicit multiply, right? This is another challenge. Actually, this is quite intriguing because if every variable in your question is all of this same format of something in something. So for example, here is monkey in zoo or animal in zoo. So it's something in something, what we call two entity, right? It is really hard for you to generate multiply or implicit multiplication out of it. Because multiplication is really, when you think about it, is like this continuous or consecutive instance dependency, where it's a chain of dependency. So for example, if you have like X classroom in a certain school, and within every classroom, you have like Y number of chairs, and then I ask you like how many number of chairs in classroom, then it's very tempting for you to multiply X by Y, right? So it is really formulated using this consecutive chain of instance dependency. So the solution for us is also very easy, is that we introduce one further chain, one further level of dependency, meaning that we introduce this newborn children per adult lion in zoo. So that well, rest of them is two entities. So here is one additional one. So then the problem formulates as the number of lions in zoo equals to 7. The average number of children per lion in zoo is 2. So what is the total number of lions or animals? Say the zoo only have this lion, one type of animal. Then you are very tempting. Very tempting to multiply 2 by 7 to have this implicit multiply. And so now we have plus and multiply. So how do we generate the rest of them? So subtract and divide, right? Although we found these operations to be very ubiquitous actually in GSM-AK, but previous work seems to not cover this very much because of certain practical limitations that I will introduce in 1 second. So basically, you can still use the previous method to generate minus and divide, but you will soon realize that if you generate them just like randomly perturbing the graph, you soon leads to negative results for minus and also floating point numbers for divide. So if you have this like irregular numbers in your realistic context and you feed it to LLM, the LLM will quickly, it's very tempting for LLM to generate nonsensical stuff saying that, the problem is not practical, so I refuse to solve it, something like that. So for us, we really want everything to be in integer arithmetic. We want everything to be controllable. There is actually a very neat technique we get away from this problem. We call it reverse mode, meaning that we generate. So essentially, of reverse mode is that we generate, subtract, and divide using plus or multiply. Meaning that, so you have this, previously we talked about how to generate this plus, right? You have basically 1 and 2, these two conditions, and you generate 3. Right now, we perturb the sequence of the condition versus the query. Say we give you 1 and 3, and then ask you about 2. So then it is natural for you to conduct this negative or subtract. The similar things for divide as well. So previously, it is 1, 2 given 3, 1 through and ask for 3, and now we give you 1 and 3 and ask you about 2. So then it's natural for you to carry out this divide. So the thing we want to stress here is because in our generation, so everything is generated constructively, meaning that we generate first the instance variable, assign it with concrete value, and then go on to the abstract value, abstract parameter. So if we perturb it, we make sure everything is still integer, and the divide and subtract actually make sense. They give sensical numbers instead of negative and floating point numbers. Actually, so further mapping from the graph to natural language actually requires a lot of work, kind of tedious work. So the first thing is what we talked about is like we want everything to be integer, and we also don't want the LM to get tripped by just calculating stuff. We don't want LM to fail the question because they cannot do like 5-digit number multiply another 5-digit number. So that's why we kind of limit the range of numbers to say 3 digits, so couple hundred by couple hundreds at max for OP OP less than 30. And we also want the language to be understandable by the LLM. So we avoid realistic concepts like locations, person's name, and also when we write about the variables, we avoid saying A is B because the chain can get very annoying long. We write something in A or something per A. Yeah. And also because we want to impose the minimum constraints to our graph construction, we want the graph to grow like randomly without constraint. We also ensure that every variable can assign to another variable, meaning that we align their units. Yeah. One of the fundamental problem with synthetic benchmark is that it's still quite limited in semantics, meaning that everything is still feels programmed. So to really do our best in solving this or alleviating this, at least, we introduce several templates actually to the problem. So previously we basically talk mainly about the animals in zoo or animals in a location, right? This is the first template. We also introduced some other templates like teachers in school and also movie festival. On the right, we kind of show a case study of using Llama 3.1 8D model to just evaluate them on these 3 different templates. So the goal is basically we don't want everything to be directly identical, but we want to introduce some diversity into it, but we also don't want it to be like very, very diverse, very, very different. So you can see on the right, they all follow the similar trend, and also they have some diversity. So using the generator right now, we are able to generate both the explicit and also implicit relationships of all of the 4 fundamental operators, which is basically covers the entire GSM-AK data set. And then we use this generator to kind of generate. So the generator is like purely software, so there's no LMs in it, right? We generate some evaluation examples from the generator, and this synthesized data is what we call GSM-Infinite, right? And the big thing about GSM-Infinite is that it is purely software, and also it is like LM understandable, and also I will argue it is human understandable, as I will show some examples. So here is a slight nuance here is that originally we want to have like 3 different sub partitions. So one is easy, so meaning that it only contains everything explicit. And one is medium, meaning that it only contains explicit plus implicit plus or minus. And one is hard. So but we then found that to cover, like, say, those very performant reasoning models with only easy tasks, you actually need to scale up your ops to a very large number. That leads to the generation of these LLMs to exist a 4K API output limit. So we actually make easier slightly harder and call it symbolic, basically meaning that instead of asking a value of a variable, we first provide a value and let the model to select all of the variable that equals to that value. So kind of like VT, yeah. Here are some examples on the right, and also on the left shows the positioning of GSM-Infinite. You can take a time and look at the example on the right. So so on the left, basically, kind of the target of GSM-Infinite is to cover all of the pink, or I will argue pale red region on the left. So as you can see that traditionally all of the like reasoning problems, they are short context, right? So for GSM-AK, the average context of the problem is like 70 tokens. For math is like 50 tokens. And also for the long context benchmark, they are usually, as I said, they're usually of very low reasoning complexity. So GSM-AK is trying to like give you this freedom and also this fine-grained controllability over this region. The only caveat is that because we only cover the grade school level math problems, So in order to have very strong or very high reasoning complexity, we have to sacrifice the context, meaning that the problem needs to get a bit long in order to cover this. So this is kind of the positioning or our understanding of GSM-Infinite benchmark. So also, like we talk about the short context runs, right? We should talk about how to generate reasoning problems, but how do we extend them to long context, right? Actually, so on the left shows a schematics of our method. So say we already now have this short context problems, right? These are the nodes and edges are like in blue and green. Right now we have a bunch of noise, right? We have a bunch of noise variables. But how can we make sure that the noise is closed semantically and also it cannot be solved easily by RAG? We actually found that if you have massive amount of edges going from the core graph to the noise nodes, you can actually achieve that. This is kind of what we called a spider topology because it looks like a spider. On the right, we show kind of a visualization of a random AK problem we generated. Yeah. So here is a more concrete example. So say this is I think this is like a 4K problem, or even less than that. So the yellow ones are actually the context you actually need, and all of the rest, the cyan, the sentences in color cyan are the noise that we added. Okay. So we argue that the problem can boost it to whatever context. Actually, right now there's actually no limit. But right now, I think the code we publish is able to do like at least 2 million tokens actually. Okay, so I think we all familiar with this A, right? So this is our previous study of the RAG, and we also conduct the exact same experiment setup on the GSM-Infinite long context problems. So previously, we argued that RAG is very good at separating randomly injected noise versus the essential classes that is labeled in orange. But right now on GSM-AK, like GSM-Infinite long context, it actually does it very poorly. As you can see, it barely the essential classes scatter like randomly through the spectrum, so you barely really grasp which sentence is like important, which is not. So on the right, we empirically measured so long context LM, so the same old 70B model, and with this 2 RAG baseline. So you can see that the gap between the 70B model versus those two baseline is like incredibly large, or pretty large actually. So this is basically what we want. We want a benchmark that is really kind of long context RAG only viable, right? Is only doable by long context LM instead of RAG. Okay, so then we have basically the benchmark that is both zero noise and long context. So now we then use the benchmark to evaluate a bunch of very famous and also very strong models. The core metric we used to measure them is area under curve. So basically, as you can see that for every op, we can generate many problems. So in real world, like when we actually do it, for every op, we generate like 200 problems, and we evaluate an LM on those 200 problems, and we plot a dot corresponding to that op. And we do that for ever increasing operations as long as the accuracy stays above a threshold. The reason we want to set this threshold is to avoid like waste of compute because plotting the entire spectrum sometimes requires a lot of stuff. And once the performance falls below 5%, say, we just terminate the evaluation. So this is the leaderboard we have for the zero noise. So by zero noise, I mean like we don't inject any noise. So it's like we don't have those noise nodes and edges. And we evaluate, I think, 18 very strong, I will consider very strong models. So the yellow highlighted one are all reasoning models. And the rest, the white one are actually non-reasoning models. And we also have some hybrid models, hybrid architectures, for example, Minimax and Jumba. So I think for hybrid architectures, they still faced some degree of difficulty when solving very complex tasks. And another thing at least I'm amazed is that the gap between these reasoning models versus non-COT models is actually otherworldly like, meaning that I think the gap is actually quite huge, right? It's sometimes quadruple the score. So this is the long context. So for us, we only do 8K, 16K, and 32K. As I mentioned, we can generate longer, but is that for the models that we have the budget to evaluate. If we evaluate, say, 16 4K and 128K, is that the score are basically very, very low. So we choose not to do that at the moment. So on the right, we plot the price of the generation. So the dollar per million token generated on the x-axis, and in the vertical axis we have 16K context performance, and also a zero noise. So the diameter of each ball is the zero noise. So one thing to highlight is that the DeepSeek V3 is actually very good model at the zero noise. But if you go for longer context, their performance is not comparable to, say, Gemini 1.5 Pro. Okay, here are some more fine-grained nitty-gritty of some ablations to the study. And one more thing is that so right now we're still growing the leaderboard. So because we are an academic lab, so we don't have the budget to like do all of the fancy models. So say right now the long context model don't have reasoning. We will add DeepSeek R1 very soon, but say if you have the resource and you are interested in putting your models on board, please contact us, and you can visit this website for the up-to-date leaderboard. Yeah. Okay. Next slide. Okay, so right now let's go into kind of more in-depth study of the evaluation and a little bit ablation. So one thing that we found is like incredibly interesting is that when we plot the shape of all of the performance degradation of different models. So here we plot the Quinn 7B, 72B, and also O1 Mini. You can see that the significant difference of the COT model versus non-COT models, and also across different model size. A very intriguing thing we found is that the LM performance degradation is exponential, meaning that at some point you look onwards, it's exponentially decreasing. And for realistic tasks, so for medium and hard, we found that the loss landscape or the loss or the degradation can be fitted well by a sigmoid function. So here's the R square value we plot. It's actually bigger than 0.98. Okay. Another thing is that because of the unique design of our benchmark, we are able to separate the reverse thinking problems. So the problems that goes from abstract to more concrete, versus always forward thinking, meaning you always constructively do stuff. Is that we found that the LLMs are innately very good at doing forward thinking problems versus reverse thinking problems. So this is the blue curve of the forward thinking, and the reverse, the orange curve for the reverse. Well, we plotted 5 different models, but our website actually provides you a visualizer, so you can visualize all of the specific plots, and you can have fun doing that. Okay, this is a noise ablation that I also found very interesting. Is that so basically, we also need to inject noise, but the thing is, our noise is very semantically close. So to study this noise, we also have 2 more ablations. So one is very interesting. So we just ask the zero noise problem to the GPT-4o, and ask it to generate some noise that it thinks is very relevant. So it's like for Zhou is like commentary of the it's like a figure commentary, and for random is like VT, right? The sky is blue and the grass is green. The takeaway is that we found that RAG is actually doing better at this other noise compared to the long context LLMs. Well, this is understandable because when your context is filled with a lot of garbage, and so it really impacts the LLM's ability. But if you RAG is filter out all of these garbage, you are left with very clean problem. So it does make things more easier for LLM to solve. Versus the blue curve is actually our close noise, is that we show that RAG 70B model does have an edge over over RAG. So here are all the plots that we have for the long context. So basically for every plot, we plot the zero noise, the 8K and 16K and 32K for every model on a very detailed subtask. So 10 models, 3 different subtasks, so 30 models in total. We found that LM performance tend to drop very sharply as context length increases, but different models exposes different, like very diverse patterns. So feel free to check out the ablation studies that the page of our paper for if you are curious into it. Okay, so we also studied the repeated sampling of the data set. So repeated sampling has been a very heated topic recently. So I also like it a lot because repeated sampling basically we think that because of the lack of abundance of reasoning benchmarks, so when people study repeated sampling, they tend to only study on GSM-AK where you cannot fine-grainedly control the difficulty of the task, but we can. So what we do is that we use 2 different models. So one is Qwen 7B and another one is Llama 8B. So on the left we show 7B. So we scale up the inference compute exponentially. So this is 1 sample, 2 sample, 4 sample, 8 sample, 16 sample onwards. The takeaway is that we found that linear scaling. We found that exponentially increasing the compute inference cost only leads to linear scaling of the AUC of the curve. So on the right is this plot. So remember that the x-axis, the cost, is plotted log scale. So you can see that we have this very amazing like a linear scaling trend. And so the R square is actually above 99, 0.99 for both line. Okay, so thank you so much. So that's what I have for the talk, and I'm happy to answer any questions. Yeah.
Thanks, Yang, for the very nice presentation. I think we have some time for questions. So maybe while the audience is thinking about questions, I actually have maybe 1 or 2 questions to have.
Yeah, sure.
So the first question I have is, so one thing that's very nice because you have kind of like the true computation graph to some extent.
Yeah.
And I'm curious, we look at a sort of reasoning chain, if there's
Mhm.
any found in language models, is there a way, do you think the reasoning chain match the computation graph, or they have like zero correlation, for example?
Actually, it is actually pretty interesting. So we found that I think all of the models right now, all of the current generation of models right now, they have this implicit COT, regardless of whether it is like RLHF or GRPO trained or not. We found that they all tends to have this implicit COT pattern. So you can see that their generation is usually extremely like multiple times longer than our ground truth generation, because when we generate the data set, we also can generate the solution, right? Because the solution is basically a topological sort of the graph. You find the shortest path to the solution. We found that the model tends to have multiple times as lengthy as our generation, and this is even exacerbates when we evaluate some R1 distilled model where they are writing books and versus just 1 sentence. But one more thing that is very interesting, I also noticed, is that if you have like handcrafted few shot COT, so if you follow the COT paper, you have handcrafted COT for every problem, and you ask them to follow this pattern, they can generate a very short and succinct problems like solutions. So yeah.
I see. Interesting. Thanks.
Yeah, to add a little bit to the answer, or the comment, if you notice the last slide talk about a exponential in the computation, but a linear growth in the performance. So we're just saying that this some kind of test time scaling, no matter you reason in a hidden space or explicit token space, more longer generation lengths or more samples, there's something that is incorrect, which is this scaling. The good news is it still scales. The bad news is it does not scale with the ratio that we anticipated or the slope we anticipated. So there must be something wrong with, there's some wasted computation somewhere. I think this correlates with the question you're asking on, does the model reason in the same way as the problem answer? It will ultimately get there. Some of the paths will be there, but not directly. That's why we think there's plenty of opportunity. After this evaluation, we got a lot of insights on how the model do this kind of long reasoning steps. And maybe there's a way to maybe turn this data sets into some training process to supervise it to learn in a more direct or shorter pathway. Yeah, so I hope that add to the answer what
Yeah, this is actually a very interesting point. Yeah, this is a very nice interpretation about the fact that models sort of inefficient, or it scales, but sort of inefficiently scale. That's potentially Basel-Finn like scaling might be a way, but maybe there are potentially better way to scale. That's
Yeah.
actually a very good point. Maybe actually have a second related question. This is maybe a stupid question, which is in my brain somehow I think long context modeling and the reasoning are two separate things. But it seems like given this context, they're actually quite relevant. So I'm just curious, does like reasoning and look at that are fundamentally to some extent similar question, or do you think they're very different orthogonal things?
I tend to think they are actually very related because when you go through a long context, especially our problem, so because of how the noise is added to the core graph, you really need to apply reasoning because it's not like semantically how close they are because they are all connected. You have to really kind of peel through or peel the problem to have this core graph that you are actually solving. So I think it is relevant and having this long context is really important for I think in my point of view to develop this very good reasoning problems. And also for the long context for developing a long context ones, I also think is very important because you can see that if like we train a say Gemini 1.5 Pro, right? It's like tens or dozens, millions or even billions to train. It's like if your model like 10 million context length is only for solving say a retrieval tasks, then it is really not to get your buck worth, right? So it's like we want to approach the ultimate goal that we set is like solving this intellectually challenging problems of humanity. So that's why we think that we need to incorporate reasoning to long context benchmarks to make them like more worth to solve, or like fundamentally only long context LM can solve. So I think reasoning component is also a very core component for developing high quality long context as well.
I see. Yeah, this is very good. Thanks. Yeah, I'll let other also ask a question as well.
I guess I can ask a question. Thank you for the great talk. It was very, very interesting. My question is around how you are thinking about taking some of these ideas to domains and types of reasoning beyond math. I guess like one example where I play a lot with reasoning is maybe I'll put in a archive paper or some research paper into say O1 and have the model work with me to reason and understand what are the limitations of this method, what are questions about this method, and reason about how we can improve this method. And so I guess this is a different style of reasoning that doesn't have necessarily all of these, math operations. Do you think that there are other sorts of dimensions to reasoning that you're looking to build into the future of these benchmarks, and how have you thought about that?
Yeah, I think it's a great question because when I'm doing this problem set, I really think it's getting more and more intense. The thought is that I think reasoning cannot be only encapsulated by GSM-AK problem or grade school math problems, because I think grade school math is only very tip of the iceberg. Is that you can basically like GSM is basically a starting point, right? You can have very all sorts of like very hard problems. For example, common sense reasoning, which is very different from arithmetic, right? As you talk about. So I think a really rudimentary idea or like a very coarse idea of mine right now is that I want to build things block by block. So say right now. We have this arithmetic reasoning or GSM level reasoning problems, and the next step is maybe do math problems that are slightly higher to kind of bounding the box and have some limited search space. But I do think like I think the whole like paradigm or the whole philosophy behind building a synthetic data set to evaluate a certain type of ability is very doable. It's like it is I think it will be very helpful not only for the community or arithmetic reasoning. So I think it is still doable if you want to build a synthetic benchmark for say common sense reasoning or even coding or other things. Yeah.
I think I see the question in the chat. So one person asked in the physics of language model math version, did creating synthetic data on GSM by adding the back token to ultra experiments. So there might be some way to create training data based on this.
Yes. Yeah, I think it's a great question. So I think in physics of part 2.2 is what he mentions is that so basically there's a claim in the paper that's saying that the LLM is able to identify its own reasoning flaws on the fly. So if they generate a false reasoning claim and they probe the LLM right after the claim, and to see if the LLM realize that it generates this claim. The LLM is like nearly 99% capable of doing that. Yes, I do believe that because I think the core difference between GSM-Infinite and so the physics of LLM construct, the main difference is that if you look at their construct, it's mainly for pre-training set, meaning that everything that they impose very not so realistic constraints to make sure that they can generate this type of data sets. But we kind of bridge the gap between this very rudimentary search space and graph generator to kind of the real world real LLM, pre-trained LLM doable tasks. So yes, you can definitely apply the same technique over there to here to generate your own training set. Yes, and actually, speaking of that, because my next step is actually doing this. I'm trying to enlarge the search space for the graph to be able to see whether this philosophy leads to a very high quality, training set just for like reasoning learning.
Nice. And then there's another question that just popped out earlier, which is I think the chain of thought graph you show seems like a way to develop a sense of scope to the context of information. So if I squint my eye hard enough, it's pretty similar to the natural structure of the code, given that you have talked about potentially in the future, building the training set where you have natural answers for the reasoning process that you have. Could you maintain a similar behavior you currently have, but within code? Perhaps where you have a track to variables, and how it changes as you go through the series of functions with many different levels of scope being applied. And then, yeah, apologies if this is a little bit off track, but you sure it's very cool project.
Okay, yeah, I think it's a great question, because when I talk to compiler guys, they also say that in compilers they have this syntactic trees, which is kind of similar to kind of the computation graph. Yes, I think the syntactic benchmark, this philosophy can be migrated to code. But yeah, I'm also very interested in it, but it's just that every time I think about it, I don't have like concrete plans of or concrete thoughts that how to bridge this gap. But definitely it is doable. And if you are interested, maybe reach out to us, and maybe we can discuss it further.
Awesome. I think we're right on time, and I don't see more questions from the audience. If not, oh wait, there's a new question. But yeah, so the same person asked, how do they reach out to you?
Yeah, just the easiest way is just to go to the archive paper, right? And we link our email there. Yeah, this is the easiest way.
Yeah.
Yeah.
Maybe. Yeah. Okay. So the person said, thanks.
Okay, got it. Yeah.
I think he meant who do I reach out? You can reach out to Yang.
Oh yeah. I think I can just reach out to me. Yeah. I think I think my name. Yeah. If you see my name on the Zoom, yeah, you can link my name to the paper. Yeah.
Yeah, and I think probably Xinyu posted the paper
Yeah.
in the beginning of the chat. So I think you can just click the paper. I'm sure there's a content information in the paper somewhere. Yeah. Awesome. Great. I think it's right on time. I think so I'll stop sharing. And this was